The methods that we've explored up to now are inherently integrated rate law approaches. That is to say, we're going to take a measurement of the concentration of A as a function of time and analyze that measurement to see if it matches an integrated rate law. What I want to do now is shift to a different approach, which is using a differential rate law to determine what the rate law is, and we'll find that this actually can be extended beyond unimolecular reactions to treat reactions of any molecularity. So let me first give the basic approach for these kinds of methods. These, by the way, are called initial rates methods, and you'll see why in just a moment. Okay, the whole idea is that we're going to initiate a reaction, and we're going to do this with known concentration of our reactant. So I'll just say with known concentration A. Now I'm going to do this initially for a unimolecular reaction, and then we'll extend it to a higher molecularity after we've done that. Okay, so we've initiated the reaction with known A, and we're going to then measure the value of this concentration A at some later time. I'm going to call it delta T. Okay, so this is a short time interval later. All right, and it's important that we're doing this as a short time later, because what we really want to do is to take this value that we have measured and use it to evaluate the rate. And I'll remind you that the rate we can identify as -1 over the stoichiometric coefficient of the time derivative of this concentration, and we're going to approximate that as 1 over this stoichiometric coefficient times this difference A0 minus A delta T divided by delta T. Now you may wonder, I've got those reversed. I removed the minus sign. I've basically just done 2 steps in one by converting this minus sign to reverse the order of these two concentrations. Okay, once we've done that, we're going to repeat and do this for a different starting initial condition. All right, so what would this look like? Let me draw a graph to kind of illustrate exactly what it is we're doing here. Okay, so we're going to be looking at the time dependence of reactions, and we're going to be essentially looking at the concentration as it changes. Now, we're running several trials, so let me indicate that just by choosing several points up here on this vertical axis where we're going to start. And the whole idea is that if we have a lower concentration, it's going to be probably a slower rate. So it's going to come out like this. A little bit higher concentration will come down at a little bit faster rate, and then the highest concentration will start at a much steeper rate. All right, and come out. I haven't drawn this very well, but I think you get the idea. Now, what we're measuring in this experiment is essentially we're trying to get an idea of what the slope is here at the very beginning of the reaction. So you can see that it changes in each of these cases, and we get a slope that's more gradual as we lower that rate, because the rate, in some sense, is going to be equal to some constant times this concentration raised to a power. Now, we're starting off with initial concentrations, and we're only measuring the rate right here at the beginning of the reaction. So we have very good control over the concentration of A at the time that we measure this rate. And that's the whole point of doing these initial rates calculations. All right, so this is going to be our operational definition now for the rate that we're measuring experimentally. So the whole idea is we're going to do a couple of different trials. So let's see what that looks like. Okay, so if I do 2 trials, and let's say that my initial concentrations I can write as A01 and A02. I'm continuing with the 0 to indicate the time, but I want to differentiate these two. They're different initial concentrations for A. Okay, so for the first reaction, I might measure a rate. I'll call it rate 1, and it would simply be equal to the rate constant times this initial concentration raised to its power. Okay, I then might run a second trial, and that would be rate 2, and again it will be given by this, but now I have a different concentration here. All right, now I have these two expressions and I have some unknowns here. The order of the reaction is unknown and the rate constant are unknown. So both of these are unknown numbers. How can I separate them? Well, since the k is the same in both cases, if I were to divide these two equations, so in other words, I'll just take the ratio of these two equations, the k's are going to cancel out. So I'll lose that, and I'll end up with an expression that looks something like this. I'll have rate 1 divided by rate 2 is equal to the ratio of these initial concentrations, which again are ones that I have set up, raised to the n power. All right, so now we have known quantities on this side, we have known quantities here. The only thing that's not known is this exponent. Now, I'll mention that a lot of times if you are clever in the way you choose these, for example, if you choose the A01 to be twice as large as A02, it's pretty easy to tell if the rate here is twice the rate of 1 is twice the rate of 2, or the same as the rate of 2, or 4 times the rate of 2. It's pretty easy to figure out what that integer is. But if, in case you haven't used a clever set of initial conditions, I'll simply mention that if I took the log of both sides, it would enable me to solve for this rate, for this exponent, and it would be given by the ratio of the log of the ratio of the rates divided by the log of the ratio of the initial concentrations. All right, so there's always a way that I can get this number. And I will say if their number should turn out to be something that's not quite an integer, these numbers are meant to be integers most of the time. Sometimes half integers, but most of the time they are integers. So if you get something like a 1.07, you can call that 1 and be relatively secure in your choice. All right, so this looks like it's pretty easy to apply for a single reactant, so a unimolecular reaction. What would we do if we had multiple reactants? Well, in that case, there's a couple of ways that we can proceed. So we've got a reaction now that is implicitly A plus B goes to products. And what I want to do is to use an approach like this somehow to isolate the order in both of these reactants, because my rate law now in general is going to be given by K times A raised to the n sub A power and B raised to the n sub B power. So I have two orders that are unknown as well as the rate constant here that's unknown. So how would I do that? Well, one way I could do it, and I want to focus on A because I've already got expressions here for A, but if I wanted to focus on A, one thing I could do is I could have B in an extreme excess. In other words, a really large concentration of B and a smaller concentration A, a much smaller concentration of A. This is something called the isolation method. And essentially what it does is it ensures that the concentration of B is not going to change very much during the course of this reaction. If A is very small and B is very large, only a small amount can react to form the products over here. So the B is going to be relatively constant, which means that most of the thing is going to look like the rate law that we had up here for for this unimolecular reaction. Okay, we can subsume the concentration of B into the rate constant, if you will. All right, so that's one way we could do it. But there's another way we could do it if we're not satisfied with just having a large concentration of B, and that is that we could simply run several trials in which the initial concentration of B is the same for each trial. So imagine, say use same B0 for different trials. So if this is my rate law, and I'm using the same concentration of B, you can imagine setting up two rates as we did before. So I'll have rate 1 is equal to K times my initial concentration of A, and I'll again denote these with a 0, 1, now raised to its power, and B, and it's going to be the same in both cases, so I don't need to distinguish that. Rate 2 will be a similar expression. Okay, but now notice, even though we don't know n sub b, it's the same in both of these equations. So in fact, these two quantities are exactly the same in both of these trials. The rate constant is the same in both of these trials. So if I took the ratio of these two rates, I'm actually going to get an expression that looks exactly like this. So once again, I can just use this mechanism to solve for n sub a. So I'll just put that here, solve for n sub a, the same way that we did it before. Well, if I can do this for a, I can do the same thing for b. And so the whole point is that I can use this same strategy to also solve for n sub b. All right, so this way I'm going to get the order of this chemical rate process. I haven't looked at an integrated rate law. I've done this purely with the differential rate law to get this. Now, what about the rate constant? Well, in both of these cases, I can find the rate constant by simply plugging in the values that I've gotten for the order of the reaction and use it in one of the trials. So, for example, I've got an expression here that relates a rate that I've measured, a concentration of A that I know, a concentration of B that I know, and I've solved for these two exponents. So I've got everything except for K, and I can solve for K. And so K is simply going to be the rate divided by A raised to the NA power, B raised to the NB power. And I can do this for any of the trials that I've run for this reaction and find the value of K. Now, I will tell you that solving for K in this way doesn't result in the most precise value for K, but it gives you a good rough idea. You're certainly going to be right in the order of magnitude of K, and you might have one or two significant figures for K. But this is a great method to use, very flexible, and can be adapted to many different kinds of equations, many different kinds of chemical reactions.